by using multiple. Okay, we can increase the data rate by transmitting our information from different antennas, right? So instead of transmitting only one antenna, we can transmit from number of antennas. It will increase our data rate. So it has some other consequences as well. So we have some antenna interference and co-channel interference. Those things, those type of things are there. But still, so we have a lot of benefits of using MIMO in communication. I think so that motivated the researchers to use MIMO in radar as well. In radar, okay, so we have a lot of benefits, okay, so of using MIMO, and there are two categories, okay, so that we use, okay, so there are two categories of MIMO that we use, okay, so in radar. One is the widely spaced MIMO radar. In widely spaced MIMO radar, what happens, okay, so we use, okay, so multiple radars, okay, so at different locations, and each location is widely separated, okay, from the other location. So what benefit, okay, so we get, okay, with this one, okay, so we get a diversity gain, right? And similarly, we can get rid of the scintillation effect as well. What is the scintillation effect? For example, if a target is coming, okay, toward the radar, if it will change, okay, so a tiny his angular location, okay, from its mean location, so it will create a very high signal to noise ratio at the receiver of the radar, right? Okay, that make it very difficult to detect the radar, right? So, but of course, if you use, of course, multiple widely spaced MIMO radar, we can get rid of these type of things, right? So I think, so during the war, because between Pakistan and India, so maybe in May, okay, so I think it's very famous, and there maybe 2 or 3 articles are there. Okay, so they use, okay, so this concept widely spaced, okay, so MIMO radar, and I think it was very effective. And the second one is the closely spaced MIMO radar. In here, okay, so what we do, okay, so we use, okay, so multiple antennas, and we place them, okay, so very close to each other. But usually, okay, so we put them, okay, so lambda by 2 at a distance of lambda by 2 from each other. So this is how, okay, so we place them. And what benefits, okay, we get, okay, so with this one, okay, so we get, okay, so high spatial resolution. We can resolve, okay, so different targets, okay, that are very much close to each other. And then, okay, so we can suppress the jammers as well. And then, okay, so it provides us flexibility to design, okay, desired beam patterns. So we can achieve, okay, so variety of beam patterns, and we can achieve variety of beam patterns, okay, so through a software, right? So we don't have to change, okay, so any hardware. With the help of software, okay, so we can achieve, okay, so different beam patterns, right? Okay, so I think where it is used, applications, I think in fighter planes, okay, so fighter planes, okay, just like, okay, I think in Egypt, okay, so you have Rafale in F-16, and in J-10C, I don't know whether you have a J-10C in Pakistan, okay, so we have, okay, so J-10C, okay, so in these fighter planes, okay, so they use, okay, so the concept of MIMO radar, they call it ISA, I think active electronically scanned array. In here, okay, so what we have, okay, so we have independent antennas, and those antennas, okay, so they are very much closely, I think, placed. In here, okay, so if you see, I think, you can see, okay, so in the first top left figure, you can see there are multiple antennas. Okay, so in F-16, okay, so the number of antennas, okay, so they vary, okay, from, depending on the model, okay, they vary, okay, from 1,000 to 1,500 TR units. And similarly, if you go on the right hand side or top one, okay, so you can see, okay, so there are the missile seekers. The examples of that is the Meteo, okay, which is used in the Europe by Eurofighter. And then in Chinese one is the PL-15. They have, okay, so they have got, okay, so electronically scanned or MIMO antennas, okay, so inside them to detect the targets. Right. In here, okay, so the number of antennas, okay, so they use, I think, is classified, but okay, so I think, okay, so what I read, okay, so they say that they use, okay, 16 to 64 antennas, okay, so in the missile. Similarly, if you'll see, okay, so the bottom left figure, okay, so here, okay, so we have surface to air missile system, right? Okay, so this system, okay, so it tracks the targets, and if they find target, okay, so they try to destroy, okay, so that target. Okay, so the example of this one is the Russian S-400, okay, so that system, right? Okay, so then we have in the Navy, okay, so we use, okay, the MIMO system, okay, so we use, okay, so in there as well, right? I think because in the war, because it was not used, so I don't know about the Navy ship, because which it will be. I think on the Indian side, I think they have, I forgot the name, I think what was the name of that ship, right? Okay, now, okay, so I mean here, why we use the concept of MIMO to achieve the beam pattern, right? Okay, so why it is important, right? Okay, so I think we will start, okay, from the isotropic antenna. We know that you can, if you have an isotropic antenna, so it transmits power, okay, so in all the directions, right? Okay, for communication, okay, so it's okay. Base station initially, okay, so we don't know where the user is, right? So we transmit, okay, so power, okay, so in all the directions, right? Once, okay, so we know the direction or the location of the user, okay, then we focus our power, okay, so in that direction. In radar, okay, so we know that, okay, so the enemy, okay, so it can come, okay, from this side, right? So we don't have to transmit power in all the direction. Okay. The second disadvantage of such type of radiation is that, okay, so if there will be some reflection, so since, okay, we are transmitting in all the direction, we will not know that, okay, from which side the target is coming in or the aeroplane is coming in, right? So, and the third disadvantage is that it should transmit power in all the direction, right? Okay, so then, okay, you have to transmit, okay, so lot of power, right? So that, okay, so you can see, okay, so target, okay, so at far distance. So with this one, you cannot see, okay, so at the far distance. To see at the far distance, okay, so what we do, okay, so we use, okay, so parabolic antennas. Okay, so parabolic antennas, what they do, okay, they transmit the power, okay, so in the focus, they transmit power, okay, so in one direction. Right? Okay, so what they do, okay, so they transmit power in one direction. If target is present, okay, so what will happen, okay, there will be some reflection, okay, from that direction, okay, then they will move, okay, so on the other direction. If target is present, okay, some power will reflect from that target. Otherwise, okay, nothing will be reflect. So this way, okay, so we can not only detect the target, we can also tell where the target is, right? The disadvantage of parabolic and you may have seen, okay, so this type of radar, okay, so on the airport, maybe on the old airports, okay, so you may have seen, okay, so such radars. Here, okay, so we can transfer more power in one direction. We can find the direction of the target as well. But there are some disadvantages as well. The first disadvantage that, okay, so here, okay, so we need, okay, some mechanical part, okay, to rotate, okay, this one. Due to that, okay, the life span of such radar is quite low. So what can be the other solution? Okay, the other solution is the phased array. Yeah, other solution is the phased array. In the phased array, what we do, okay, so we electronically scan our beam, okay, so in different direction. So how it work? Okay, so first, okay, so we'll see, okay, so if you have multiple antenna, so what will happen, okay, so I think if I'm transmitting x1 of n from the first antenna, x2 of n from the second antenna, and so on. If I'm transmitting in this way, then what will happen, okay, so if P is the target, then what will happen, okay, so I will receive one signal from the from the first antenna, and then I will receive a second signal from the second antenna. But okay, that signal, okay, so there will be some phase shifting in that one. Similarly, from the third antenna, there will be double phase shift, okay, so, right? And so on. So there will be some phase shift in this one. And mathematically, if you have to write, okay, so we can write, okay, so in this one. So AT theta is we call it steering vector, and X of n is the transmitted signal vector, right? So depending on theta or psi, so what will happen, okay, so at P, okay, so we can receive, okay, so maximum power, or we can receive, okay, so minimum power as well, right? So if phase is aligned, all the phases, okay, so they are aligned, okay, so we'll receive, okay, so maximum power. If the phases, okay, so they are not aligned, okay, so they are out of phase, okay, then, okay, so we will receive, okay, so minimum power, right? So what we can do, okay, so to maximize the power, okay, so in one direction, in the direction of P. For example, if there is a target at the direction at P and the direction angle is psi, so how we can maximize this power? So there's a question how we can maximize this power. Okay, for that what we can do is we know that, okay, the signal that we are receiving from different antennas, okay, so all of them, they are phase shifted. If before transmitting a signal from from any antenna, if we can maybe add, okay, similar phase to cancel the effect of, okay, that phase, okay, that will appear due to that antenna, then, okay, so we can maximize the power, right? So this what, okay, so we do, okay, so in the phased array radar. In the phased array radar, okay, so we have X of n, and then, okay, from second antenna, we know that, okay, so I think there will be some phase shift, all right? And what I do, okay, so I think here, okay, so I add or subtract, okay, the phase, okay, corresponding to the same as this one, right? So I think then what will happen, okay, so at P, okay, so all the waveform from different antenna, okay, so they reach, okay, so at the same time or in phase, you can say, right? So here, okay, so I have shown on the left-hand side in the in figure B, okay, so I have shown the beam pattern. Here you can see that, okay, so at 20 degree, I think here, okay, so the phase was the angular location, okay, so it was 20 degree. So we receive, okay, so very high power, okay, so at 20 degree. Right? So this how, okay, so phase array radar, okay, so it works. Here, the advantage is that, okay, so you don't have to mechanically rotate, okay, so your whole platform. So what you can do is, okay, so here you will use, okay, phase shifter, phase shifter 1, phase shifter 2, phase shifter 3. You will just, okay, so change the phase and you can rotate, okay, your beam, okay, so in different direction. So what can happen, okay, so if you have to maybe, okay, so see, okay, so in two different locations, I think with this job, okay, so it becomes, okay, difficult, okay, for this, for the first phase array radar. And secondly, okay, so we have the electronic phase array radars. In phase array radar, okay, so the phase shifters, okay, so they have limited dynamic range as well. You cannot change the phase, okay, so from say, okay, so -90 to +90, okay, so they have some limited range, right? So these are the disadvantages in phase array radar. So for that, okay, so what is the other solution? The other solution is the MIMO-Radar. I think here, okay, so we'll talk about the concept of MIMO-Radar. In MIMO-Radar, okay, so we don't use, okay, so any phase shifter. So what we do in here, I think first, okay, we'll see, okay, so for example, if at P, the same equation as we have previously, okay, so the signal that I will receive, okay, so at point P, okay, so can be written by this equation, right? So if I want to find the power, what will be the power, okay, so at this location? So what I have to do, I have to take the absolute value, I have to square it, and then, okay, so I have to take the expectation of this one. So if I'll do this one, here I have to take took the absolute value, then I square it, and then I have to take the expected value as well, right? So you know that, okay, here we have expected value of the steering vectors, okay, so they will not change at all because, okay, they will remain same. Here, the only thing which is changing is the transmitted waveforms. So here, okay, so if I'll expand this equation, I can write, okay, this equation in this one, and this thing is nothing but the covariance matrix or the waveform that we are transmitting, right? So here P psi is equal to steering vector, then we have a covariance matrix, and then again, okay, so we have a steering vector. I think if you see, okay, this equation, what you will find that the power that you are transmitting in the direction of psi, it depends on the covariance matrix. And by changing covariance matrix, okay, so we can achieve, okay, so different beam. We can achieve, okay, so different beam, okay, we can focus our power in different direction. But the main problem is that, okay, how to find, okay, so this are for the, for example, if I want to achieve, okay, some specific beam pattern, right? So here, if I will, you should see, okay, so R, okay, so it will look like, okay, so this one. In here, okay, so rho 1, 2 is the correlation or the correlation, okay, so between the waveform that we are transmitting from the first antenna and second antenna. Similarly, rho 1, 3 will be the correlation between the first antenna and 3 antenna, and rho 1 M will be the correlation between first and mth antenna. So this way, okay, so we have bunch of things, okay, so that we can change, and by changing, okay, them, we can achieve, okay, so different type of beam pattern, right? So now, okay, we will see, okay, a few examples in here. For example, if all the waveforms, okay, so they are uncorrelated. Uncorrelated means, okay, so there is no correlation, okay, between any two waveforms. So if you have this type of situation, okay, so then the covariance matrix, okay, it will look like this one, right? And now if I'll see, okay, the power in the direction of psi, okay, so if I'll put identity matrix in here, what will happen? Okay, so here we have a steering vector, here I have a steering vector. If I multiply the Hermitian of the steering vector with the steering vector, what I will get? I will get the size of the steering vector, which was the M, I think, number of antenna, right? So I think here, so what this equation says that, okay, so if the correlation or covariance matrix of the waveform is identity, or all the waveform, okay, that you're transmitting from different antennas, okay, so they are independent, what will happen in that case? Okay, so you will be transmitting power in all direction. I said this is the same case as we have, okay, so in the case of isotropic antenna. Isotropic antenna transmitting in all the direction, right? Theoretically, so if you are transmitting independent waveform, okay, so you are transmitting in all the direction. Now we'll see, now we'll see, okay, second case, okay, so R can be like this one as well. So in here, all the waveform, okay, they are fully correlated, right? So all the waveform, okay, they are fully correlated. Okay, in other words, you can say that I'm transmitting same waveform from all antennas. So if you'll do like this one, then, okay, so P psi, if you solve this equation, this equation with r being all the values equal to 1, then okay, so we will get okay, this equation. And you know about this one, I think this is similar to the sink, right? And sink, the maximum value of this equation, okay, so will be at size equal to 0. So this equation, okay, so it will transmit, or this setup of covariance matrix will transmit the power, okay, so it will focus the power in the both side direction or in the 0 direction. Because here I'm assuming that this is 0, and here if I'll go on the right hand side is plus 90, if I'll go on the left hand side is minus 90. So this, if all the waveform, okay, they are fully correlated, I'm transmitting, I'm focusing my power, okay, so in the both side direction and very narrowly. So what happens, okay, so in the case of phased array radar, in the phased array radar, as we have earlier seen that, okay, so we transmit x of n, and then from the second one, okay, so we phase shift, okay, so that waveform. And then again, okay, so the waveform that we transmit from the mth antenna, okay, so we again, okay, so we put some phase shift, okay, so we m-1 time for phase shift, okay, so in here as well, right? Right. Okay. So I think if you'll see the covariance matrix, okay, so it will look like this one, right? Here, I think in the previous example where I showed that all the waveform, okay, they are fully correlated, okay, so in that case, what happens, okay, so you are transmitting power, okay, so in the both side direction. Now, in here, by changing psi, okay, you can change the beam pattern, okay, so in different directions, right? But here, I think the only degree of freedom, okay, the only thing that we can change is psi. So the only thing we can change is psi, and by changing psi, okay, so we can steer our beam, okay, so in different direction, right? So this is the basic equation of the phased array. Okay, now again, okay, so I'll go back to the MIMO. Okay, so in MIMO, what we have in MIMO, okay, so we have a number of parameters, okay, so that we can change, right? And if we change, okay, so them, okay, so by changing them, okay, so we can achieve different beam patterns. And here, if you will count, okay, so I think this part, the upper diagonal elements, okay, so they are the conjugate of the lower diagonal elements, right? So if you will change them, okay, so you will change them as well. So I think if you think, okay, so in this way, then, okay, so we can change, okay, so only them. And if you will count, okay, so how many parameters, okay, so we have in here, okay, so that is the degree of freedom. And what for example, if the size is m, okay, then the degree of freedom, okay, so we'll get is the m square minus m divided by 2. I think minus m is due to this one, so we have to subtract, okay, so these one, because from here, okay, so this represents the power that we are transmitting from different antenna. Okay, so this represents the power that we are transmitting from the first antenna. This represents, because I think this is a row 1, row 2. I think the multiplication of the waveform, okay, so itself, because which is the power, right? So we want to transmit same power from all the antenna. If you want to transmit a different power from different antenna, if you allow, then you will get more degree of freedom. I'm saying that I want to transmit same power from all the antennas. So in that case, what will happen? Okay, so I will get, okay, m square minus m divided by 2 degree of freedom. If m is equal to, let's say, equal to 10, then it will be 100 minus 10, 90, and divided by 2, 45. So we will get, okay, 45 degree of freedom compared to phased array radar. Here, what we'll get, okay, so we'll get more degree of freedom, and here we don't have to use, okay, so any phase shifter. Only you have to play with the waveform. By playing with the waveform, okay, so we can achieve different beam pattern. Now, okay, now the second question is that, okay, so how we can get how we can achieve, okay, these beam patterns. This is very simple. So here we know that, okay, this is the power. If R is the covariance matrix, this will be the design power. So this is my design power. And if I define, okay, so my beam pattern by psi theta k. Psi theta k mean if I have divided, okay, from minus 90 to plus 90, this degree minus 90, and here, okay, so I think I have a 0 here. And at some locations, I want to transmit power. In other location, I don't want to transmit power. I want to transmit 0 power. Or this can be one beam pattern. This can be one psi theta k. And similarly, it can be, for example, if I don't want to transmit power, okay, so in the middle direction, I want to transmit power, okay, so in the side lobes, right? So this can be the other desired beam pattern by so here. So we have set up a problem, okay, so by minimizing the difference, but this is the design, and this one is the desired. So by minimizing the difference, okay, between these two with respect to R, we can achieve, okay, so different beam patterns, right? But here, actually, it's not that simple. Since, okay, R is a covariance matrix, and all the covariance matrix, okay, they have to fulfill, okay, some condition. We know about this one. Okay, so I think the chorus matrix, okay, so it should be positive semi-definite. And secondly, what I mentioned, okay, so earlier, if you want to transmit same power from all the antennas, okay, so what we need, okay, so we need same all the main diagonal elements, okay, they should be same, right? So here, okay, so we can make that same as well, right? So we provided a number of solutions. So if you're interested in the solution, I'm not going in this solution, but I think this is the main problem. This is the setup of the problem, right? So I think you can see, okay, so this paper, because this is my first paper that on MIMO-Radar, because you can see this one and you will find, okay, so number of algorithm in here. The earlier researchers, okay, they proposed, okay, so proposed a reduced solution, because I have proposed earlier researcher, they proposed iterative and constrained optimization solution. So I propose unconstrained and non-iterative solutions. Okay, so in this paper. So actually, once, okay, we have the covariance matrix. Okay, the second work is to design. Okay, sorry. I think here, okay, so I have provided a few examples in here as well. In here, the green curve, okay, so it shows the desired beam pattern, and the blue curve, okay, so it shows, okay, so the beam pattern that we have achieved, okay, so using our algorithm. Here, okay, so I wanted to transmit, okay, my power, okay, so from -30 to +30. In here, okay, so I wanted to transmit power, okay, so into side lobes. In the third one, I want to transmit my power, okay, so asymmetrically, okay, so only in one direction, okay, right? So we have achieved, okay, so this one, right? Okay, now, okay, so once we have the covariance matrix, we don't transmit the covariance matrix. Okay, what we have to do, we have to transmit the waveform. So we need, okay, waveform that can realize, okay, that covariance matrix. So this is second step. So first, okay, so what we do, okay, for the desired beam pattern, okay, so we find the covariance matrix. Once we have the covariance matrix, in the next step, what we do, okay, so we find the waveforms. To find the waveform is very simple, I think. So what you can do is, okay, so if you have an R, you can find the square root matrix of this R, and then you can multiply this square root of matrix, okay, with the some orthogonal waveform matrix, or in the orthogonal waveform matrix, you can use the Hadamard matrix as well, right? So you should multiply this with this one, and you can define the length of your waveform as well. So this will give you X, right? So you can get X, okay? So X is the waveform, okay, that you have to transmit from different antennas, right? Or you can also use X is equal to square root of the matrix. You can use the Kuliski decomposition for that one, or you can use, okay, so MATLAB, in MATLAB, okay, so we have command, you can use that as well, and that will give you the square root matrix. Once you have square root matrix, okay, so even if you multiply with this matrix or with X of G is the matrix of Gaussian random variables, right? Independently and identically distributed Gaussian random. If you multiply with them, okay, so what you will get, okay, so you will get your X as well. I think it's very simple to understand as well, I think. Okay, for example, if I'll take the first equation, okay, so if R1/2 psi, okay, so if this is my waveform, and to achieve the covariance matrix, what we have to do, we have to multiply X with X Hermitian. If you multiply X with X Hermitian, okay, so in other words, okay, so you multiply this R1/2 and then waveform matrix, and waveform matrix is the orthogonal matrix. And if I'll multiply X Hermitian, which is phi Hermitian and R1/2. So phi into phi Hermitian, okay, so it will be, since, okay, so all the waveform inside phi, okay, they're orthogonal. And then, okay, so what will happen, okay, so in the middle, okay, so we'll get identity matrix. Again, okay, so we'll get R, right? Similarly, in here, if Xg is the Gaussian random covariance matrix, you should multiply Gaussian random variable covariance matrix, matrix with X of G. Okay, so what you will get, since, okay, all the waveform, okay, they're independent, right? What you will get, okay, so you will get identity matrix. Again, okay, so you will get R in here as well, right? The only problem here is that I think, okay, so if you will design a waveform by using this equation or this equation, the waveform, okay, they will look like, okay, so this one, right? So they may have a very high peak to average power ratio, right? So we are familiar with the waveform just like the BPSK, okay, or QPSK, or those type of waveform. Those have finite alphabets. I think if you have to transmit, okay, this type of waveform, okay, then you need, okay, so very expensive power amplifier. So that has very a high linear region, right? With small linear region, cheap power amplifier, we cannot transmit, okay, such waveform. I think we have the similar problem, okay, say in OFDM as well, right? So we need, okay, so this type of waveform, BPSK waveform, okay, so we have +1 and -1, right? To achieve this one, so what we did, this. I think here, okay, so I think, what I'm assuming is x1 and x2, okay, so they are Gaussian random variables, and y1 and y2, okay, they are BPSK random variables. Okay, so the relationship is can be we can draw a very simple relationship, okay, between these two. Okay, so if I'll take the sign of x1, if x1 is a Gaussian random variable, what I will get +1 or -1. Similarly, if I have this one, again, if I'll take the sign of the Gaussian random variable, I will get a BPSK symbols, right? Now, okay, so if I define rho 1, 2 is the correlation between y1 and y2. y1 and y2, okay, they are BPSK random variables, and x1 and x2, okay, so they are Gaussian random variables. So the correlation between BPSK random variable is this one, and Gaussian random variable is this one. And we already know about the relationship, how to get, okay, y1 from x1. We know about this one, right? So by using, okay, so this equation, we can find the relationship between the cross correlation, right? So when we solve, okay, this equation, I think this is a very simple equation, because you have to just, okay, put the values in here. So we get, okay, this equation. So this equation says that if you have Gaussian random variables, those are the correlation, okay, between the Gaussian random variable is rho m of n. Then the corresponding correlation between the BPSK random variable that you will generate, okay, so with the help of a Gaussian random variable, will be rho mn, right? And this is the relation with sign will be there, okay, in the relation, right? So this is for the two random variables. If you have a matrix of random variables, okay, then relationship, okay, so this will be the relationship. If R is the covariance matrix, desired covariance matrix that we need for the desired beam pattern, right? Then we can find RG, which is the covariance matrix that we have to generate, that we will use to generate, okay, Gaussian random variables, right? So with this one, we'll generate, okay, covariance matrix of the Gaussian random variables. Once we have Gaussian random variables, okay, so what we'll do, we can generate Gaussian random variables using this equation. So once we have Gaussian random variables here, right? So what I'll do, I have to just, okay, take the sign of this one. If I'll take the sign of this one, what I will get BPS matrix of BPSK random variables. Once I have matrix of BPSK random variables, right? Then if I will check the covariance matrix of those random variables, or those BPSK random variables, okay, so that will be the desired R, right? So this way we can find, okay, so find BPSK random variable for the given covariance matrix for the given beam pattern, right? So here I have given, okay, so in a very simple way. If you are interested, okay, so in the detail, okay, so you have to read this paper. Right. Okay. So then the received signal, okay, then, okay, so I think if the received signal, okay, can be written by this one. And for here, I'm assuming that, okay, so I think, okay, so I have a transmitter. Then, okay, so on the other side, I have a receiver, and I'm transmitting using multiple antenna. I'm focusing, or I am illuminating, okay, a few targets, okay, so they are, okay, so in the atmosphere. And then, okay, so some power is reflecting, okay, from those targets I'm receiving, okay, so at the receive antenna, right? And the steering vector at the receive antenna is represented by AR theta t. The steering vector of the transmitter, okay, so is represented by AT theta t. Beta t is the reflection coefficient of the target. Okay, so we have multiple targets in here. Here, okay, so we have some interferences as well. We have some jammers as well, right? Okay, then, okay, so all of these parameters, they are defined in here as well, right? So now what I want, okay, so I want to check, okay, so how many targets are present. And if the target, okay, they may be close or they may be far away from here, from each other. Okay, for that, okay, so we can use, okay, so Kaplan algorithm, we can use Apps algorithm. There are famous equation of the Kaplan and Apps algorithm. Those are given in here. And then, okay, so we have a likelihood ratio test as well. We can check, okay, so whether the target that I have detected is whether it's a genuine target or it's coming from the jammer. I think the beauty of the waveform is that, okay, so when you transmit, right, then, okay, so you concentrate, okay, so your algorithm, it concentrate, okay, so only on those waveform, okay, that are reflecting from the target. In the jammer, what happens? Okay, so I think there is some bad guy. So what it does, okay, so he read okay what frequency you are transmitting, then because he retransmit okay the same frequency, but okay, so there is no correlation between the transmitted and received signal, right? So this is how the jammers work, right? So we can get it for that as well. So here, okay, so I have shown okay, some simulation results. In here in this scenario, okay, so there was a strong jammer. There were three targets, and those targets, okay, so they had the values of 4, 4, 4, and then okay, so 1. And with the help of okay, Kaplan and apps, okay, so we have easily directed all those targets, and you can see okay, so the how resolved okay, these targets are. I think if you use okay, so conventional algorithm, okay, they will not be okay, so that much resolved. Just like the least square solution because I have given in here, right? So I think for further reading, okay, so you can read okay, so this as well. Now, I think I'll jump on the integrated sensing and communication. Okay, first, okay, so we'll go, okay, so we'll see, okay, so what was the need for integrated sensing and communication? I think you know that, okay, so currently we have more than 7.8 billion mobile subscription and 12.6 billion IoT connections, right? And I think both of them, they are increasing day by day. Top of that, okay, so these subscribers, okay, so they need okay, so more bandwidth, and okay, so all these things, okay, they need okay, so high spectrum. And we know that okay, so I think the expensive thing okay, so in the communication is the spectrum, right? The companies okay, so they have the Vodafone, just like the Vodafone, they have to pay okay, so billions of dollars okay, so for to buy some spectrum, right? The second disadvantage is that in the future application, okay, so we need okay, sensing and communication as well, right? So just like in the autonomous vehicle and in the smart cities, okay, so we will be needing okay, so both functionalities as well. For the time being, okay, the autonomous vehicles okay, that you will see, okay, in there, okay, so what we have, okay, so we have a separate system okay, for communication, and we have a separate system okay, for sensing. Autonomous vehicle, okay, so they have to sense as well, okay, because to avoid okay, so any collision or any damage to the other vehicle, right? So what can be the solution? Okay, solution can be merging of these two technologies. We know that both of these technologies, okay, they use uh, 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 antennas, they use modulator, they use okay, demodulator, okay, so right. So these type of things are in there. So that suggests that okay, we can combine these two as well, right? Okay, so by if you combine okay, these two, okay, so we can get a lot of benefits. Okay, so we can save a lot of resources, we can save a spectrum. Otherwise, okay, so we have to give some spectrum okay, to sensing function and some spectrum to the communication functions, right? In the application smart cities, in smart cities, okay, so we know that okay, so we have to do the surveillance, and okay, so during the surveillance, okay, so if you find some suspicious activities, okay, so we have to inform, okay, so we have to communicate those suspicious activities, okay, so to the base station as well. So if you can do okay, these two things, okay, so in the same spectrum using same hardware, okay, so that will be great, right? But this is the application in the smart city. And similarly, in the connected vehicles, okay, so we need okay, so spectrum okay, for sensing, and we need spectrum for the communication in autonomous vehicle. Okay, for example, if there's a vehicle is going in the fast lane and but it's going slow, on the behind okay, so that vehicle there's a vehicle and he wanted to move a little bit fast, and the first vehicle is in the fast lane. So what it will do, okay, the first the behind vehicle okay, so it will communicate, it will first okay, so it will sense, yes, okay, whether okay, so I'm not too close okay, to the vehicle in front of me. If it is too much close and the other vehicle is going slowly, okay, so then it will send a message to the first head vehicle that okay, so please okay, leave this lane. And then okay, so I think as a response, the vehicle which is in front, okay, so it has to leave the lane, or otherwise, okay, so the vehicle, okay, so it will send back a message that okay, there is some accident or those type of things are there, and maybe okay, there is a base station is also communicating with other vehicles that okay, please slow down, there is some accident, okay, those type of things can happen. Okay, so we need spectrum hardware resources for both functions, right? And if you use okay, different hardware, different spectrum, there can be interference, and it can be expensive, it can be bulky as well, right? Okay, so that motivate the need of combined system or integrated system where we can have both integrated sensing and communication. Due to that, okay, so in ISAC, there is a IMT 2030, okay, so standard, okay, so in the development activities. Right, okay, now I will talk about the first solution that we have provided is fully coherent receiver for DFRC. First, okay, so we'll see, okay, what is the difference, okay, between the communication and between the communication and the sensing system, right? So in in sensing, first, or in radar, okay, so what happens, okay, so we have one waveform and we transmit that waveform again and again, okay, so after pulse repetition interval. So in communication, what happens, okay, so we have one symbol or corresponding to that symbol, okay, so we generate one waveform, we transmit that waveform, and then in the second slot or in the second time, okay, so we have a different symbol, we transmit different symbol, and in the third one again, okay, so different, and we don't know about what those symbols are, because we transmit, okay, so in this way, right? So why we cannot use, okay, so this one, okay, so in communication, in sensing the communication symbols? Okay, so for example, if the target is moving, I'm interested to estimate the velocity of the car which is in front of me. Okay, so if I transmit a communication signal, right? So what will happen? Okay, so for example, if I'm transmitting a sensing signal, what will happen? Okay, so I think, okay, so I will, since, okay, so I'm transmitting the same thing, RK of t, RK of t, RK of t, and each transmitted signal, when it comes back, okay, so it comes back, okay, with a different phase, but okay, the phase is changing, okay, so linearly, right? So what will okay, so for example, if I have to find the FD, what I can do? Well, I will just, okay, so apply FFT, and after applying FFT, I can find the FD. Once I have FD, I can easily find the velocity of the target or the vehicle. So what will happen in the case of communication? In the case of communication, okay, so I'm transmitting symbols, okay, so randomly. Okay, the reflected signal, what will happen? Okay, there will be in each symbol, okay, there will be phase shift, right? In the first one, there will be phase shift. In the second one, there will be phase shift, and so on, right? And the phase shift, okay, so it will be, okay, so linear phase shift. Where the difference is coming in, right? So here if you'll see, okay, so the symbol that we are transmitting, okay, they're different. Okay, so for initially I'm transmitting +1, -1, +1, -1, -1, -1, +1, right? So I think if you'll see, okay, the received signals or received samples, right? Okay, there will be multiplicative noise. In the case of sensing, there was no, there wasn't any multiplicative noise, right? So due to that multiplicative noise, if I will apply FFT, I cannot find the Doppler shift. Okay? If I cannot find the Doppler shift, I can not find the velocity of the target, right? So this is the main difference, because between the sensing and communication. So how we can get rid of this one?
Dr. Sajid,
yes.
Yeah, sorry to interrupt you here, but we have a question. I'm not sure if we can address it now. We had a question in the chat that has the radiocentric DFRC been implemented in a real system yet? So this is a question in the chat. And also, I think we had some audience with us today willing to have going less faster a bit, because they they are not following every single detail. So if we can go a bit less faster.
Interrupt me, okay? So wherever you want, you can interrupt me.
Yeah. So if we can, so this question is radar-centric DFRC is it yet implemented in a real system?
I think the Texas Instrument, okay, they have implemented, okay. So I think I have seen, okay, so in one conference, but I think it's on the experimental base. I don't know, okay, so whether if they have implemented, okay, so in a real system that they have deployed, okay, so in real system. I don't know about that one. But okay, so I think on experiment basis, okay, so I have seen, okay, so by Texas Instrument in some conference.
Okay, perfect. Yeah.
So should I move? Go ahead.
Yeah, sure.
Okay.
Yeah.
All right.
Thank you.
I think we have less time as well, maybe. Okay. I think the solution.
I think we can still go beyond the schedule. So
yes,
we are happy to
no problem.
to stay after the time. Yeah. we are enjoying actually the presentation, so so feel free to go beyond the schedule.
Okay, sure. If you can interrupt because at any time, if you maybe if I'm not explained okay, so properly anything, okay, then you can interrupt me, right?
Sure, sure. And this is also for the audience. If you have any question
Yes,
for Dr.
for
Sajid,
everyone.
yeah, feel free to ask.
Actually,
Thank you.
I'm on the full screen. I don't see okay, so the questions, right? So
Yes,
there's a
yes,
problem.
yeah. I am coordinating this point, so no need to worry about it. Yeah, thank
Okay,
you.
okay. Maybe I think later on if you ask me. Okay.
Sure.
So how we can solve that problem? Okay, so in here, I think if you see in here, okay, so we have multiplicative noise here. Okay, +1 minus, if all the values, okay, they are +1, okay, there's no problem, right? Okay, but here, okay, so they are changing, okay, so it is becoming a multiplicative noise. Due to multiplicative noise, okay, so after applying FFT, we cannot estimate the Doppler shift. Or if we cannot estimate Doppler shift, we cannot estimate the velocity, right? Okay, so I think now I think so we are looking for a way that, okay, so I think yes, okay, these are changing, but I think if can we process them such that, okay, so they don't change. Okay, so all of them, okay, so after processing, whether I'm transmitting +1 or I'm transmitting -1, okay, the thing that I get, okay, so is the same, right? So for that, okay, so we provided one solution, okay, for that. I think, this was the setup of the problem or the cost function. In here, what we do, okay, for example, okay, first, okay, so we have to decide how many symbols, okay, so we are, what modulation scheme you are using. For example, if I'm using, okay, BPSK scheme, what I'll do, okay, so I'll design two filter. One filter will be for +1 and second filter will be for -1. And what I'm constraining is, okay, so for example, if I'm transmitting +1, when +1 will pass through H1 from the first filter, right? Okay, so it will give me one response. Then, okay, so when I'm transmitting, okay, so -1 from the second filter, right? So it will give me some response, right? So what I want, okay, so I want the same response from those two filters. All right. So this is what, okay, so I have done in here, right? So here what I'm saying is, okay, and we can have, okay, so number of modulation scheme. We can have BPSK, QPSK. Here, okay, so I have given one example, okay, so where we have K symbols, right? So this is my constraint, or what I want when I will multiply my symbol X1T with, when I convolve H1 of T with filter H1 of T, I will get one response equal to the x2t h2t and equal to hkt hkt. If we can make this one, then we can solve, okay, that problem that we had, okay, so earlier in here, right? Multiplicative noise. If we have, okay, this type of system, okay, so if we can solve, okay, this problem, we can design the filters, we can solve this problem. Here, okay, so we have provided the solution. Again, okay, for the derivation, full derivation, you have to see, okay, so this paper underneath. Here, okay, so I have provided few simulation results. Okay, so I think here, okay, so we have compared our performance, okay, so with the iterative method algorithms. I think here you can see that, okay, so I think the response of here, okay, so I think what we assume that, okay, so there were 4 alphabets, right? And you can see that, okay, 4 colors in here. In our algorithm, we proposed, okay, 2 solutions. One was the linear convolution method, second one was the circular convolution, and here again we have 4 filters, right? And the response of all 4 filters, okay, so is same. I think you can see from here. And as a consequence, okay, so you can see the benefits in here. Okay, so the iterative method proposed by other, I think it's very difficult to detect the targets. But with our 2 algorithm, with the first algorithm, it's quite easy. With this circular convolution is even more easy, right? And again, okay, so we can achieve, okay, so good, okay, better performance as well with this one. Now, okay, so now I'll talk about now. Okay, so I will try to combine MIMO-Radar with the ISAC, right? So in here, okay, so we have the beam pattern invariance coarse matrices, right? So now, I think now, okay, so hopefully, okay, you'll be familiar with this equation. Okay, so this is the power that we are transmitting in some direction, right? Now, okay, so we have decided that, okay, I want to transfer my power, okay, so in some direction, right? So what will happen, okay, so I think, okay, for that, okay, so I can design some waveforms. And I have designed, okay, some waveforms. But you know that in communication, when I transmit waveforms, right, okay, so I don't have any control on the waveform. If I change my waveform, okay, then what will happen? The beam pattern, the covariance matrix of those waveforms will change. If the covariance matrix of the waveform will change, what will change? The beam pattern will change. That we don't want. right? You understand this point? Hopefully, yes. No, okay, later on, yes, class, right? So, okay, so I want to embed my symbols, okay, that I'm transmitting, but okay, I don't want to change my covariance matrix. But you know that, okay, so when you change your waveform, that you change your symbols from different antennas, okay, covariance matrix will change, right? So but okay, we don't want to change, okay, the beam pattern. I want to transmit my power in same direction. Either I'm changing, okay, so my symbols or not, right? Here, if I expand, okay, this equation, I think you will see, okay, so this is the equation, okay, that we will get, right? Here, okay, so R11, R22, RMM, okay, these are the diagonal elements, and row 1, 2, row 2, 3, row M-1M, and this is the first upper diagonal elements. This is the second upper diagonal elements and third upper diagonal elements, right? So these are the diagonal elements. And here, from this equation, we can conclude that if I change the covariance matrix of the waveform, but I don't change the summation of the diagonal elements, my beam pattern will not change. It's obvious from here, right? So this way, we can transmit different waveforms, right? And beam pattern will not change. Why beam pattern will not change? Because we are not changing the summation of the diagonal elements, right? So this was our one solution that we have published in this paper. You can go through this one. I will share, by the way, I will share the slides as well, okay, later on. Okay, so you can go through again. Okay, so what I'm saying is, I think here, okay, so I have one covariance matrix, R1, right? Okay, so this is the main covariance matrix. And then, okay, so if I change C with G, here, by changing C and G, okay, if you check the summation of the diagonal elements, they are not changed. If they are not changed, okay, beam pattern will not change. But okay, so you have different covariance matrix. So one covariance matrix can carry one information. Second covariance matrix can carry second information. Similarly, we can have other as well, C plus epsilon and G minus epsilon. Now, I think you should add these two. Okay, it will C plus G. It will remain C plus G. Whatever the value you will select, okay, for epsilon. So this will not change. It will remain same. The summation will remain same. If the summation is same, okay, beam pattern will not change. So this way we can input or we can embed our information in covariance matrices. Okay, so one covariance matrix, okay, so it will take another one information. Second covariance matrix will take another information. But if we fulfill, okay, this condition that the summation of the diagonal elements is not changing, okay, so we will achieve the same beam pattern. Beam pattern will not change. Here, I have just given one example here. Okay, this is the main covariance matrix, and then if you add these two epsilon minus epsilon, and here I have epsilon. If you check the summation of this one, it will be 2 gamma. Here, gamma plus gamma is 2 gamma. Here, gamma plus gamma 2 gamma minus epsilon and plus gamma 2 gamma. Right? It will not change. Here, by changing epsilon, okay, so I can generate different modulation scheme. Okay, so in the first one, okay, so what I did, I choose, okay, so 0.2. I choose 0.2. My beam pattern is not changing, will remain same. But okay, so my covariance matrix has changed. Second, for the second one, okay, so I choose the value of epsilon is equal to 0.8. My covariance matrix has changed, but my beam pattern, it will remain same. So this was the BPSK. Similarly, we can generate number of modulation scheme. Okay, so for example, for QPSK, what I'll do, I'll choose, okay, for the first covariance matrix, I will choose 0.2, for second 0.4, for third 0.6, for fourth 0.8, and so on. We can do like this one. The only problem here is that, okay, so I think at the receiver, okay, so we need, okay, so all the covariance matrices. I think it's same, okay, because in any modulation scheme, the receiver, okay, so receiver knows that, okay, so I think what modulation scheme, okay, so my protocol is using, okay, so whether it's using BPSK or QPSK, and he knows that, okay, BPSK in BPSK. What he's expecting, he will expect, okay, +1 and -1. Similarly, okay, so we can tell the receiver that, okay, so you can expect R1, R2, or R1, R2, R3, R4 for QPSK scheme. You know, those type of things we can do that, right? But here there is one problem in here. I think the bit error rate performance, okay, so it depends on the distance between covariance matrices. If the distance occurs between covariance, for example, like in the case of BPSK, If I generate so one covariance matrix, then I generate second covariance matrix. If the distance between them is high, my bit error rate so it will be very good. If it is very much close, bit error rate so it will not be very close. It will not be very good, right? So this is the disadvantage. Now, now I'll go for the second method, communication by embedding information in covariance matrices. Here we know that so R is the covariance matrix. We can generate so R will be R. We can define so R as X into X summation, right? So we have already seen so this one. Here, if I use with X, if I use another matrix, the psi matrix, the capital psi matrix, right? And psi matrix is like this one, right? And I have generated a new X tilde matrix, right? The covariance matrix of X tilde and X will remain same. It will not change. Why? Because when I multiply X tilde with X tilde Hermitian, I will multiply this with the Hermitian of this one. And when I multiply this with the Hermitian of this one, what I will get? I will get identity matrix, I will get the same covariance matrix, right? So we can put some information in here as well. Here, so you can put information. Here you can have BPSK, QPSK, any PSK modulation scheme, so you can use so in here. This how so we can transmit, we can embed our information that we want to convey to the user by not changing the covariance matrix. If you're not changing the covariance matrix, we are not changing the beam pattern. Right. So now, so how the receiver will decode, so what has been transmitted, so he can, we can see that, so received signal, it will be HK theta. Here I am assuming that, so the HK is the channel coefficients of the user from the transmitter, right? So I think, for example, if I have multiple antennas in here, there will be a H0 will be from the first antenna to the user will be H0, from the second antenna to the user will be H1, H2, and maybe HL, something like that, right? So by using so this one, by using this one, this equation, so we can, and then so by minimizing the difference between this and this one, we can easily find the symbol that we have transmitted, right? And there is another method. Should we stop or okay? So I think this is the last method. By the way, this is the last method by which we can embed our information. For that, so I think I have given two preliminary equations. In the first one, I think this is the transformation. Okay, so this is the transformation. What it says that if U and V have equal norms, right? If U and V have equal norms, then the transformation T, so it will yield these results. So what it will do, so it will multiply T with U, it will give you V. If you multiply T with V, it will give you U. It's called the Rodriguez rotation, right? The Rodriguez rotation formula or transformation, right? And secondly, the second equation is this one. In this equation, we are saying that so if we have any complex vector, we can split that complex vector so into its amplitude and into its phases, right? So this is what we can do is. Now, here we know that so we have a R0. R0 is the covariance matrix, and this covariance matrix, so it will give me a specific beam pattern, right? So what I did, so I split or I split this covariance matrix using the square root transformation, and here so I have got the square root of this R, and if you if I have S0, right? And if I want to transmit, and here, so by the way, previously I assumed that so my X, I think previously I was saying X, so X was the matrix of transmitted symbols or transmitted waveforms, right? So here I'm saying, so my S is the weight matrix. Right? We can transmit our information by two ways. In the one, so for the covariance matrix, corresponding to that covariance matrix, we can find a matrix of waveforms. And in the second method, what we can do is, so we can find the square root of that matrix, and when we multiply this square root of matrix, so with some matrix phi, which is the orthogonal matrix, so we can achieve so different waveforms as well, right? So in the first one, so previously what we did, so we directly found the waveforms. In here, we are assuming that the square root matrix as a weight matrix, and by multiplying this weight matrix with orthogonal waveform denoted by this one. Okay, so we can again, okay, so we can design the waveform, right? Because we can transmit the waveform. So these are the transmitted waveforms. Okay, they will be this one, and S naught is the square root matrix, and phi of t is the matrix of orthogonal waveforms, right? So we achieve this one. Now, okay, so if S naught gives me R naught, if I'll multiply S naught with UK, if UK is the unitary matrix, what will happen? Okay, so it will not change the beam pattern. Beam pattern will remain same, as the covariance matrix will not change, because S naught UK Hermitian, if I'll multiply this with UK Hermitian into S naught Hermitian, UK into UK Hermitian, okay, so again, okay, so it will become identity matrix, and then okay, so we have S naught and S naught Hermitian, which is again the R naught, right? So in this case, what will happen? Okay, so if I'm transmitting I can transmit S naught. If I'll transmit S naught, this will be my received signal at the user. If I'm transmitting SK, my received signal, okay, so it will be this one, right? So if this is my received signal, if I demodulate, okay, this signal with each orthogonal waveform, so then what will happen? Okay, so I will receive, okay, these samples at time k, right? So this will be a snapshot k, right? Okay, so I will receive, okay, so this signal, right? Here, okay, so I'm assuming that SKT and AT conjugate theta, okay, so is equal to M of k, which is a vector, right? This is the vector. Now I will further expand this one. What I will do, I'll put the value of S of k from here. S of k, you know that S of k is S naught U of k. If I'll put S of k is equal to S naught U of k, what will happen? Okay, so we will get this one, right? And by the way, remember this one. What is M of k? M of k is, I think, if I ignore the noise and I ignore the attenuation, M of k is the received signal by the user. So M of k is the received signal by the user, and we can write, okay, so S of k, which was this one without noise and the attenuation. And when I replace, okay, so S of kt with this one, S naught t and UK of t, okay, so what will happen? Okay, so this will be the equation. Now I'm assuming, okay, so S naught t and AT conjugate theta. Okay, this is M naught. I'm assuming that S naught t, AT conjugate theta is equal to M naught, right? Then I'm splitting U of k. Okay, so UK A, UK B, UK C, like this one, right? So M of t is the transmitted signal, and M of k is the received signal, right? Now M of k is the received signal. Now how until now I have not embedded, okay, so any information in my signal. But until now we know that, okay, so if we'll change, okay, so if U of k is unitary, then what will happen? Okay, my beam pattern will not change. My sensing function, okay, so it will not change. My sensing function, okay, so it will remain same. So here what I did, okay, so I assume that U of k, I'm splitting, okay, U of k in 3 unitary matrices: UKA, UKB, UKC, right? And what I want here, I think, okay, so I want to find the values of UKA, UKB, UKC in a way that, okay, so I receive on this side, on right-hand side, I receive M of k, right? So we know that, okay, so we will receive, okay, so M of k, but I'm saying that, okay, now I will find unitary matrix in a way that my right-hand side is M of k. That I want. Now we know that M of M naught. Okay, so we can split, okay, so M naught, which is a complex number, M naught, okay, can be written by this equation, right? I can split, okay, so M naught by the phase matrix and the amplitude vector as well, right? And one thing more here, I think we have MK here and M naught here. The norm of MK and UKT M naught, it will remain same until unless UK is a Hermitian matrix, UK is a unitary matrix, right? So that we know, right? So if I'll put, okay, this value, so what will happen? Okay, so we know that now, okay, so this is M naught, and I'm assuming UKA is equal to this one, which is the opposite or the Hermitian of this one. If I'll assume UKA is equal to this one, then when I'll put UKA at this place, what will happen? Okay, so this will cancel out. If this will cancel out, okay, so what will be remaining? MK will be, which is MK is this one. MK will be equal to UKC, UKB, and only amplitude part will remain. Okay, so this part will cancel with UKA, which is this one, right? Now what we have UKB and UKC. Here, what I want, and now, okay, I think now it's please okay, remember that UKA is a unitary matrix, right? Because this is sure UK is a unitary matrix. Now we have to find UKB, UKC. They should be unitary matrix, but okay, so they should give me on right hand side M of K, right? So here, okay, so what I have done, okay, so I'm assuming that, okay, so I want to transmit +1, -1, +1, -1, and -1, -1, -1. So this is my M of K. I already know about M of K that I want to transmit. I want that's what this should be received, okay, so at the receiver, that I want. So in this way, okay, so we can pre-assume that, okay, so I'm transmitting, okay, this M of K. So in here, again, okay, so what I'll do, okay, so I'll use, okay, so the rotation transform. Okay, so UKB is equal to this one. This is the rotational transform here, right? If I'll use, okay, UKB a rotational transform, what will happen? If we'll go back, UKB is a rotational transform, and if I'll multiply and rotate, how I generated, okay, this rotational transform with the help of M0 and MK, right? So I have used MK and M0. So if this is the if this is the rotation transform, and this rotation transform is multiplied with this one, so what we will get? I think we will get MK. So in these two, instead of these two, okay, so what we'll get? Because we will get MK. We will convert, okay, so M0 to MK. So here with this UKB, okay, so we'll get this one. And now I think it's very simple to make it MK is equal this side MK, which is the again, okay, so which is the phase part, and then we have amplitude part, right? So UKC, okay, the only thing missing is the phase part. So now I can assume UKC is equal to this one, which is again a unitary matrix, right? So this way, okay, so I can find, okay, so I can embed, okay, my information in M of K, and on the basis of M of K, I can find UKA, UKB, UKC, and all of them when we combine together, okay, so we get, okay, UK, and UK is a unitary matrix. So this way we are not changing our beam pattern, but okay, so we are embedding our information, right? So this was the last one, and further reading in here. So summary, yes, so MIMO-Radar was the new technology, right? It provides us, okay, so a lot of degree of freedom. We can achieve, okay, so different number of different beam patterns, and what else? Yes, so ISAC provides way to use same resources for communication and sensing. That's it. Thank you. Questions?
Thank you so much, Dr. Sajid. And I think we have a question from
Yes.
Daniel Peters. Yeah, please go ahead.
This is Daniel. Am I audible?
Yes.
Yes.
I can
Yes.
hear you.
Excellent presentation. Very detailed. Question for you. It seems that in radar, the way I understand it, the shorter the pulse, the higher specificity of the identification of the target. But isn't that also then limits the amount of symbols that we can have in the pulse? So at the maximum range for a radar, what is the maximum bit rate that could be achieved at the maximum range?
Maximum range. I think that we have to calculate, okay. So I think we have to calculate that. So I think if you give me the range, okay, then I can tell you, then we can calculate that one.
Well, I guess that what I'm trying to highlight is at the maximum range, you have very little bandwidth left over. And if we're using the shortest pulse.
Are you talking in terms of from ISAC or from the other thing? From where you're talking about?
In either way, in other words, embedding symbols in the covariance matrices. That method
okay.
of
All right.
Yeah.
Okay.
So I guess
I think the question is two parts, right? One of them is what is the maximum range, right? And what is yeah, okay.
A radar will have a maximum range. That's a given. So that's why I'm putting that constraint. In other words, I don't want to give you any flexibility. I'm trying to find out what is going to be the minimum, the maximum bit rate at the maximum range where it's most highly constrained. In other words, I don't want to give the designer, the clever professor, any wiggle room. I want to know what I have to design at. Am I only get 1 bit per pulse, or am I going to get 128K? These are the types of questions that a system designer would have to get from his radar person.
Right, right. Yes, I think here, okay, so for, I think different system, okay, for example, okay, so if you go in the first one, just second, in okay, I think normally, okay, so what happens, okay, so I think for the range, okay, so I think, for example, I think I'll talk, okay, so in terms of resolution. If you have more bandwidth, right, okay, so you have more resolution.
Right.
Right. And
Correct. No, that's clear.
in here, okay, so I think for example, okay, so if the length of your signal is very high, right? Okay, so if you have a spreading code, if it's something like a spreading code type of waveform, because you are transmitting, right? So in that case, what will happen? Okay, so I think your resolution, okay, so it can increase. You can have, okay, so very good resolution.
Right. So if your resolution is very high, then your pulse is very short. Is that true?
Pulse is short. There are two things, okay. I think you can, I think when you use, okay, so the FMCW radar, in FMCW radar, okay, so the range resolution, okay, so it depends, okay, so on the bandwidth of your signal, right? So the bandwidth signal is very high, okay, then, okay, so range resolution, okay, so it will be very good.
Okay, well, then let me move to my last question, which is, how does the target reply to the signal? If, in other words, how does the target confirm reception of your transmitted data?
No, I didn't get your question.
Sure, there's two. There's a transmitter.
How the user will, how the transmitter will know? Oh, sorry.
No. In other words, okay, so there's a transmitter, and and then we have a target. The target is supposed to first, the transmitter will be able to detect via its receiver on board, will detect the presence of the target. Now, the transmitter, your intent is to communicate. The whole point of this is for doing communication. So you wish the transmitter, the radar, will transmit data in its pulses. The question is, how can the target signal to in the same band or in the same realm, not with a separate not with a separate transmitter of its own? How will the target signal signal at a minimum correct reception of the data, or number two, maybe additional information in reply to the radar transmitted data?
Okay, I think, okay, if I correctly understood, okay, this is your question. Okay, so I think, okay, so we have a radar. Okay, so okay, so I think I have got, okay, some users. Okay, so I'm right. And then, okay, so I have got, okay, some targets as well, right? Okay, so I'm transmitting my information, my signal, and my signal, okay, so it will reflect, okay, from the target. And then, okay, so on the other side, okay, there are some users as well, right? And okay, so they will receive their symbols.
I love that. Yes, the targets will receive clearly your radar signal.
Yes.
How do they signal the radar device? Yes, I have received your data correctly. Or even better, how can they signal back? Here is a response to the data you sent me. In other words, they have their own answer. A sensor could say a temperature value, a pressure value, or something. How does that happen?
You mean, okay, so how the user will communicate with the radar, or with the
how will the target
system?
How will the target communicate back to the radar?
Why the target will communicate with the radar? Why?
Well, okay.
Because we are detecting the target.
Love target. That. Yes, we love that very much. But the point is, you want to communicate. Oftentimes, communication is bidirectional. And there are many system important reasons why it's bidirectional. Number one, confirm reception of the data that was transmitted. How?
Okay, for that, okay, yes, the user, okay, so maybe user, okay, so he can transmit, okay, so his information back to the fusion center or back to the base station, okay, so using the usual means of communication. because the
Okay,
user,
well,
okay, so he don't have to detect, okay, so anything. He has to just, okay, communicate, okay, so with the base station. So he can communicate with the base station because he don't need, okay, so any special thing for that.
I understand that. Okay. Well, it would be nice if he could communicate somehow on the same channel as that you're all. In other words, there is already signal
No, I think
coming back.
yes, I'm talking about the downlink. I think from the
Of course.
base station to the user. For the user, I think user is not user don't have to be sensing and communication user. I think the user, okay, so he can transmit back. Why not?
And out of band. Well, that's clear. Yeah, that was already pre-existing. I guess new work would be enable the target to somehow send the data back on his reflected radar signal. That would be substantially interesting.
Okay.
That would be a covert channel back that would be difficult to intercept by a eavesdropper. Okay, thank you. Very interesting presentation.
Okay.
Thank you so much for the question. I think it was more also into the application of this. So whether the receiver and the data receiver and the target are the same or not. So I think this was mainly the question of Daniel. So whether the target can feedback something and also whether the target and the users are the same or different. But I think in your case, Dr. Sajid, I think the target is different from the data receivers, right? So
yes.
So
no,
yeah.
target. I think here, okay, so I meant, okay, the target. Okay, so target is the aeroplane, or it can be a car, okay, so which is, okay, so going, okay, so in front of the vehicle, right? So my target mean, okay, so I want to estimate. Okay, I want to estimate, okay, so its location. I want to estimate, okay, so its speed, right? Okay, so whether it's coming towards me, it's going away from me. I think that will be one way. For the communication user, okay, so user where I want to transmit my information. For the target, my target is user is not my target, right? So there, okay, so I just want to communicate.
Yeah, it's clear. Yeah, it's clear, and also a nice question from Daniel that we can think about it actually. I think. So I think we have another question from Dr. Ahmed. Please feel free to unmute.
Thank you very much. The talk was very interesting and in detailed explanations. So I would like to be thankful for Dr. Sajid. I am an old man from dealt with radars in early 70s and the 80s while it was in vacuum tubes. So perhaps I may have a question from application point of view. From your experience, what are the expected figures for main lobe jamming suppression and side lobe jamming rejection in comparison with traditional radars, especially which were equipped with ultra low side lobe antennas? And I have dealt with these ultra lobe side lobe antennas. The side lobe level was about minus 50 dBc. Thank you.
I think here, okay, so I think how we suppress jammers. Here, okay, so we transmit, okay, so I think you can say that, okay, so some waveforms that are known, okay, that are unknown to the jammer. In the conventional system, what happens, okay, so we transmit a pulse, we don't, okay, so encode, okay, those pulses. Here, okay, so we encode, okay, those pulses. So when we receive, if the jammer person, okay, so he don't know about the encoding, all right? If he know the encoding, because yes, then it will be a similar system. But if he don't know about the encoding or the cross correlation, okay, between different waveforms that we have transmitted. And by the way, okay, so we can change, okay, so these cross correlation, okay, so from time to time, just to dodge the jammer. So I think the way of tackling is different. Okay, so in the old system, okay, they were transmitting electromagnetic wave and of some frequency, and the jammer people, okay, so what they were doing, okay, they were transmitting the same frequency. And when you receive, okay, so at the receiver, okay, so you receive a very high signal, okay, so at the receiver. And on the basis of high signal, you can assume that, okay, yes, okay, the target is coming from this direction. Because your antennas, okay, so they were detecting, okay, the pulses, okay, from some direction, right? So in our case, okay, so we are transmitting, but okay, so we know that, okay, so what we have transmitted, what was the correlation, okay, between different waveforms. So somehow, okay, so we check or we compare, okay, those cross correlation, okay, so the with the received waveform with the transmitted waveform. If the cross correlation, okay, so matches, then we suppress. If
Okay,
there is no, if there is no correlation, okay, so between the transmitted and received waveform, okay, so we can perfectly jam them.
I'm just asking about numbers. If you, because I am a field, I have worked a lot with radar systems, so I have to compare figures to know the payoff of doing such complicated technology. You see, ultra low side lobe antenna worked excellently against anti-radiation missiles, for example. So how about this MIMO?
Well, actually, we just did some signal processing. I haven't maybe calculated, okay, so those numbers in number wise. No, we don't have.
Thank you. Thank you very much.
I have a question.
Okay. Yes, please.
What's the advantage in a civilian application that, you know, it would be better than just using a separate channel, one for communication, which we can achieve higher bandwidth in, and one for sensing, with a phased array, for example, which is already a tested, or like, let's say, a cheaper alternative. I'm not sure about the MIMO cost in the market, but I think the array, phased array, has been in the market for a long time, and we have cheap solutions for civilian uses. So if we cannot achieve the jamming immunity in a civilian application, since the encoding is public to all the users, why would it be more advantageous than just using a normal system?
No, I think, okay, so I think when I was talking about the jamming, I think it was on the MIMO-Radar. It was not, okay, so in the context of ISAC. In ISAC, I think both of them, they are different. Because ISAC is different, MIMO-Radar is different. In MIMO-Radar, we don't have, okay, so any communication. My first part. In the first part, I did not have, okay, so any communication part. And both of these functions, the correlation, okay, so, the correlation, okay, that we are transmitting is nothing to do, okay, they are not, okay, known, okay, to the user or the mobile user.
Yeah, okay, I got it. Okay, thank you. You know, my question still stands, is like, why would there be a shift in you know, technology between the phased array, which is used in like 5G, to the MIMO, which is I'm not sure about the cost. You probably know better than me.
Okay. I think the cost of phased phased array, in phased array, okay, so you need, okay, so phase shifters as well. Here you don't need, okay, so any phase shifter. Here what you have to do, you have to design only waveforms. You have to play, okay, so with the cross correlation between the waveforms, right? And you don't need, okay, so you don't need, okay, so any hardware component. Just like, okay, so in phased array, okay, so you need okay, phase shifter, which is a hardware component, and they have, okay, so limited range. And secondly, because with the help of phased array radar, you cannot achieve, okay, so number of beam patterns, right? If you want to transmit your power, okay, so in number of directions, okay, so I think you can achieve, but I think the performance, okay, so, or the mean square error between the desired and designed beam pattern, okay, so it will not be very, very good. In here, as I mentioned earlier, in phased array radar, okay, the degree of freedom that we get is only 1. I think in contrast, okay, so in MIMO, the degree of freedom that we get is, I think, m square minus m divided by 2. So we have more degree of freedom. We don't need phase shifters, right? And by only playing with the cross correlation between the waveform, okay, so we can do a lot of jobs.
But what about the, okay, so that's on the radio frequency end, but what about on the digital processing end? Will we need, you know, higher complex systems for the processing?
Yes, yes, we need a
Y-
complex system. Here we need
Yeah,
complex system.
but compared to the, you know, cheap beamformers that are in civilian application, wouldn't that, you know, increase the price? Maybe for like car systems, you'd need high processing power,
I think
which
power system, I think because I think if you have number of antennas, if you have M antennas, okay, then you have to transmit, okay, from all the antennas. In here, okay, so you will be transmitting from the M antennas. So in both case, power will not be power for the processing. You mean? Are you talking about the
yeah,
processing
yeah.
for
I mean the processing. We'll need more complex processors for this type of radar rather than
Yes,
the simpler
definitely.
ones.
Yes. Yes, definitely. Okay, so we need, okay, so yes. I think, yeah. Then, okay, so it depends. It depends, okay, so what you want. Okay, so in civilian application, if your application is not very intense, okay, so yes, you can use also phased array. But, okay, so in military, as you know that, okay, so I think no one is using, okay, so phased array, okay, so in any fighter, Eurofighter, okay, they are using ISA, okay, so in Rafale, okay, so they are using ISA. In F-16, okay, so they are using ISA. Previously, okay, so they were using because of phased array. Actually, even okay, they were not using the phased array because they were using the phased MIMO. I think okay, what they did, okay, so they
Yeah.
divided the whole region in multiple phased array units. Right, but
Yeah.
okay, in the modern system, all of them they are using the MIMO, the ISA, which is MIMO. Because
Okay, thank
each
you so much.
in here, okay, so each transmit receiver antenna unit has its own transmitter receiver.
Okay, thank you so much, Doctor.
Thank you so much. So do we have any other question? Okay, perfect. So thank you so much, Dr. Sajid, for the excellent presentation and for your time. And I think many of the attendees asked for the slides. So I would be happy if we can have the slides to share with them. And yeah, thank you so much again. Much appreciated. Thank you.
Doctor, I have one last question.
Yes,
Do you
Yeah,
have
sure.
any public
please.
lessons regarding this topic we can watch or something?
Yeah.
Sorry.
Do you have any public lectures regarding this topic?
The two
published?
topics of the MIMO-Radar and the ISAC,
Yeah.
if you can give them some
I
sort
taught,
of
I taught this course.
resources.
I taught this course to graduate students, okay, so I can send you that one. On the MIMO.
That would be very nice. Thank you so much.
Yes, no problem.
Yeah.
How can I receive it? Sorry.
Okay, I'll send to Jalal.
Yeah, I think if you are already in the list of attendees and you already registered in this, so I can send to all attendees. So you will receive it over email. Yeah.
That would be nice. Thank you so much, Dr.
Okay,
Said.
great. Great, thank you so much, everyone, and see you in our next webinar, inshallah.
Sorry, Dr. Sajid, will you do any more webinars?
Yes, if you want, okay, so I can give on OTFS. And
yeah,
that would be nice.
okay.
Yeah, it was very
Perfect,
this one was very good. I'd love to have more.
Actually, this was my I think I spent maybe 1 week ago this presentation. I already told Jalal, okay, there may be some typos and those type of things. If you have found, okay, please let me know, because I have to, maybe I did not put, okay, so any simulation results, okay, in this one due to the time limitation. Even then, I wanted to finish it because in 1 hour, but I think it took, okay, so more than 1 hour. Sorry for that. And I think that Dr. Ahmed Nazir, okay, so he asked a few questions, okay, so on the maybe practical side, right? So if you can send me those questions, I will see. I will look at those questions as well.
Anyhow, Dr. Sajid, I have go through the net and found some answers for my question, and I have sent this to Dr. Aida, and I will send it also to Dr. Galal.
Okay. I
through
think you
email
asked
so they
you asked very
can
practical questions,
distribute
but
it.
because I think
Yes.
we
It's
did talk
actually
about
one of it's actually one of our aims to bridge the gap between academia and practice. So so it's a good opportunity. Yeah.
Yeah, I have worked with Northrop Grumman and the Westinghouse for 9 years in Banha factory, and we have produced about more than 30 radar systems equipped with ultra low side lobe antennas in 80s, in early 80s, yeah. And we
Okay.
have
So,
also implemented some filters with microstrip lines and then with MEMS. Okay,
Yeah,
thank you
actually,
very
yeah,
much.
yes. I think this is the problem because I think in signal processing we don't do those type of things, and actually we don't know about those things.
Okay, but you did a good job, really. You
Thank
did a
you.
good job
Thank you.
for this
Thank you.
presentation.
I think I'll further improve it. I think further, please, please do, send me those questions. Maybe I think someone else, he asked, then I should know about those things, right?
Okay.
Thank you for asking those
Thank
questions.
you.
Yeah. Because I think those are from the core practical field.
yeah.
Okay, Jalal.
Perfect. Perfect. Thank you so much. Thank you
Thank
so
you so
much, and
much,
see you in
Doctor.
our next webinar, inshallah.
Bye
Okay.
bye.
Okay. Bye bye. See you.
Bye bye.